So for this question, we want to use the second derivative test to find all extrema. We're going to write any relative extrema as an ordered pair. So we have the function f of x equals x plus 4 over x, and we're interested in finding the relative extrema using the second derivative test. So to do that, we're going to start by finding the first derivative, and to make calculating the derivative a little bit easier, I'll write this as x plus 4x to the negative 1, and that way I don't have to use the quotient rule when calculating the derivative. So I'll calculate that derivative to get the derivative of x is 1, and 4 is a constant multiple. I'll carry that down, and I'll use the power rule on x to the negative 1. So the power rule says I multiply by the power, and then I subtract 1 from the power, so I get x to the negative 2. Simplifying, that would give 1 plus, let's make that a minus, because 4 times negative 1 is negative 4, so that's 1 minus 4 over x squared. And I want to find the critical numbers from the first derivative, because these are going to be my possible locations of relative extrema. So to find those critical numbers, I need to find where the derivative is equal to 0 or the derivative is undefined. So by setting my derivative equal to 0, I would have 1 minus 4 over x squared equals 0. So this is setting the derivative equal to 0. I would add 4 over x squared to both sides to get 1 equals 4 over x squared. I would multiply by x squared on both sides to get x squared equals 4. And I'll square root both sides to get x equals plus or minus 2. So I've got some critical numbers here, plus and minus 2. Then I want to think about where the derivative is undefined. And the derivative is going to be undefined at 0 because if I plug a 0 in for the x, I would be dividing by 0, and dividing by 0 is undefined. So at first glance, it seems like 0 might be a critical number because of this. But if we go back to the original function, 0 is also excluded from the domain of the original function, so it's not going to be a critical number. So it can't be a relative min or a relative max if we can't even plug 0 into the original function, so it's not a critical number. So what remember our goal here is to use this second derivative test to find the extrema, the relative extrema. And we've just found these two critical numbers. So these are going to be possible relative extrema. And we are going to use the second derivative and concavity to help us decide whether these critical numbers are relative mins or relative max. So just a recap of the idea here is that if our second derivative is positive, we know that our function will be concave up at that point. So having a point that is concave up and a critical number, so I'm drawing concave up and a critical number, is going to mean that we have a min at that point. And if our second derivative is negative, that means it's going to be concave down at that point. So combining concave down with a critical number means that we're going to have a max at that point, a relative max. We want to use that second derivative test, and we have to calculate the second derivative in order to find that second derivative test. So we have 1 minus 4x to the negative 2. What I did is I just rewrote that first derivative so that it's easy for me to calculate the second derivative. So the second derivative, the derivative of 1 is 0. The derivative of negative 4x to the negative 2, negative 4 is a constant multiple. And I carry that down, and I'll use the power rule on x to the negative 2. So I've got negative 2 x to the negative 3 using the power rule. If we simplify, we would have a positive 8 x to the negative 3, or 8 over x cubed. So we have now our second derivative, and I'm going to test my critical numbers. So let's test the critical number of x equals 2. If I plug a 2 in, I'll have 8 over 2 cubed, and that's a positive number. So having a positive means it's concave up. And concave up tells me that there is a minimum value at that critical number. So I have a relative min at x equals 2. And then we have a critical number of x equals negative 2. So if we calculate that in the second derivative, we have 8 over negative 2 cubed. And this is going to give me a negative. It's concave down at that point, which creates a max. So we have a relative max at x equals negative 2. So I just have one more thing to comment here. If we go back to the directions, it says to write our relative extrema as an ordered pair. So to do that, the relative extrema will be on the original function. So I need to plug 2 and negative 2 into that original function to get the ordered pair. So I've got f of 2. That's 2 plus 4 over 2. So that's 2 plus 2 is 4. So now we know the ordered pair 2, 4 is a relative min. I'll calculate f of negative 2. And that's 2 plus 4 over negative 2. That's 2 minus 2, and I get 0. So the ordered pair negative 2, 0 is going to be a relative max. Okay, so I made a mistake right here in substituting a positive 2 in for x into the function. So let's correct that. That should be a negative 2, which is negative 2 minus 2, and that's negative 4. So our relative max should be negative 2, negative 4. For this question, we want to use logarithmic differentiation to differentiate the function with respect to x. We have the function y equals to the 5th plus 5 squared times the square root of 2x squared plus 3. Now the directions in this one specifically ask to use logarithmic differentiation, and it's a technique that allows us to calculate the derivative more quickly. If we were to do this without logarithmic differentiation, we would have a very detailed process to go through. We've got a product of x to the 5th plus 5 squared, and this square root, meaning that we would have to use the product rule to calculate the derivative. Then within each of these factors, and notice what's inside the parenthesis is not just x, it's x to the 5th plus 5. So I would have to use the chain rule when calculating the derivative of that factor. And inside this radical, I have something other than x, and I would have to use the chain rule when calculating that. So logarithmic differentiation is going to make the process of calculating the derivative a little bit easier because I'm not going to have to use that product rule once I've gone through this process. So with logarithmic differentiation, the first step is to take the natural log of both sides. So I'll do natural log on the left and natural log on the right. Natural log of x to the 5th plus 5 squared, square root of 2x squared plus 3. So all of this is inside that natural log. And then I'm going to do a bunch of algebra steps related to the log. These are properties that are available to us, algebra properties that are available to us because we have now introduced a log into our equation. So the properties that I'm going to be using are the product rule and the power rule for logarithms. So when we have log base b of a product, m times n, we can write that as the sum of two logs, log base b of m plus log base b of n. And then the other one, so this is the product rule. And then we have the power rule, and the power rule allows us to write log base b of m to a power as that power times log base b of m. So changing this product to a sum allows us to get rid of the product rule for calculating the derivative. So we can write this as natural log of x to the 5th plus 5 squared plus natural log of 2x squared plus 3 to the 1/2. I went ahead and I changed the square root to the 1/2 power. So now I'm going to use that power rule to move these powers into the coefficient. So remember, so far I'm only doing algebra steps. I've got 2 natural log of x to the 5th plus 5 plus 1/2 natural log of 2x squared plus 3. And now I'm ready to calculate the derivative. Now one of the issues is that because I took the log of both sides, I've now changed this equation from an explicit form, and now all of these equations are implicit. So when I calculate the derivative, I need to use implicit differentiation, the process of implicit differentiation. So I'm going to calculate the derivative with respect to x on the left and calculate the derivative with respect to x on the right. Now on the left-hand side, when I calculate that derivative, the variables do not match each other. So I have to do the chain rule built into this. So the derivative rule for natural log is derivative of natural log of u is u prime over u. So this is going to be y prime over y. On the other side, the variables do match. So I'm just going to calculate the derivative like normal. Once again, the derivative of natural log is going to be u prime over u. So the 2 is a constant multiple. I'll carry that down. I want u in the denominator and the derivative of u in the numerator. So that will be 5x to the 4th. On the next term, 1/2 is a constant multiple. And I want to use the derivative rule for natural log. That's u prime over u. So u in the denominator. And the derivative of u would be 4x. So I'll do a little bit of algebra cleanup here. And I have y prime over y. That's 10x to the 4th over x to the 5th plus 5. And I can cancel. This 2 goes into 4 2 times, so this becomes 2x over 2x squared plus 3. Now I want to calculate the derivative, so I need to solve for y prime. So I have y prime equals y times 10x to the 4th over x to the 5th plus 5 plus 2x over 2x squared plus 3. And in this example, because the original equation was written in explicit form, I actually know what y is, so I can make a substitution and put that y into here. So we can write this as x to the 5th plus 5 squared times the square root of 2x squared plus 3 times 10x to the 4th over x to the 5th plus 5 plus 2x over 2x squared plus 3. Now, this answer on your test is acceptable, but there is a little bit more algebra cleanup that we can do to make this a neater looking answer. So I'm going to go through that process, but just know that on your test, the important part was getting to this point, calculating the derivative using logarithmic differentiation. So I'm going to continue with a little bit more algebra cleanup. And what I'm going to do is combine these two fractions together so that they have a common denominator. So we have y prime is equal to x to the 5th plus 5 squared. And I'm going to write this square root with an exponent, so that's 2x squared plus 3. And the reason I'm doing that is because some canceling usually happens with these, and it's much easier if it's written in the exponential form rather than the radical form. So to get a common denominator, I am going to have a common denominator of x to the 5th plus 5 times 2x squared plus 3, and I need to multiply this by the other numerator and this by the other numerator to combine those fractions together. So that's 10x to the 4th times 2x squared plus 3 plus 2x times x to the 5th plus 5. And I've got some algebra cleanup that I can do in the numerator, just using the distributive property and combining like terms. But I also have some algebra cleanup to do here. So you'll notice that I have factors that have the same base. So I'm going to be able to do some combining with these factors as well. So I have x to the 5th plus 5 squared over x to the 5th plus 5. So I'm going to have one factor cancel out. So I'll just have 1 left. I have one factor of x to the 5th plus 5 left. And I have a half a factor in the numerator and a whole factor in the denominator. So when I combine those two together, I'm going to have a half a factor left in the denominator. So it'll be square root of 2x squared plus 3 in the denominator. Then in my numerator, I'm going to use the distributive property and combine any like terms that I can. So that's a 20x to the 6th plus 30x to the 4th plus 2x to the 6th plus 10x. I do have some like terms I can combine. So 20x to the 6th plus 2x to the 6th is 22x to the 6th. Then I have 30x to the 4th and 10x. And I guess there's one more algebra cleanup thing I can do. I've got all even numbers here, so I can factor a 2 out. I also have x's in each one of these, so I can factor an x out. So I'll factor out a 2x. And inside the parentheses, I'll be left with 11x to the 5th plus 15x cubed plus 5. So I've got my derivative being 2x times x to the 5th plus 5 over square root of 2x squared plus 3 times 11x to the 5th plus 15x cubed plus 5. On this question, we have the function f of x equals x to the 4th plus x cubed minus 3x squared plus 1. And we want to find the critical numbers from the second derivative. We're looking to determine intervals of concave up and concave down. And we want to find any points of inflection, and of course write those as ordered pairs. So the critical numbers for the second derivative are going to be when the second derivative is equal to 0 or the second derivative is undefined. So we want to calculate that second derivative. We have our original function being x to the 4th plus x cubed minus 3x squared plus 1. So we need the first derivative before we can get to the second derivative. So the first derivative would be 4x cubed plus 3x squared minus 6x. And the derivative of a constant is 0. And then we can get our second derivative. And our second derivative would be 12x squared plus 6x minus 6. And I need to know when the second derivative is 0 or undefined. That'll give me the critical numbers. So the second derivative equal to 0 would give the equation 12x squared plus 6x minus 6 equals 0. I'll try to solve this by factoring. So I can factor out a 6, and that would give me 2x squared plus x minus 1 equals 0. Let's see if I can factor this even more. I know that the numbers that go here and here need to multiply to be 2x squared, so that would be 2x and x. And the numbers that go here and here need to multiply to be -1. So we can use 1 and 1. Let's see if we can make this work. If we make this one positive, that would give me a 2x on the outside, and if I make this one negative, I would make a negative x on the inside. 2x minus x would give me the right middle term, and when I'm multiplying these two together, I would get the right last term. So I think I've got the right factorization there. Okay, so let me get rid of this. And I can set each factor equal to 0. 2x minus 1 equals 0, and x plus 1 equals 0. I'll solve each of these equations to get 2x equals 1. Divided by 2, and I get x equals 1/2. I subtract 1 and get x equals -1. So I've got my critical numbers, which are -1 and 1/2. Now I need to find those intervals of concave up and concave down. So let me pause here because I found where the second derivative is equal to 0, but I always need to consider where is the second derivative undefined. Because this is a polynomial function, when I calculated the derivative, I also got polynomial functions. Polynomial functions have a domain of all real numbers, so there are no restrictions. So I'm not going to get any critical numbers from the second derivative being undefined. Okay, so I can't move on to finding those intervals of concave up and concave down. I'm going to build my number line using the critical numbers that I just found. You want to make sure that you put those critical numbers in order from smallest to largest. So we put the -1 and the 1/2. We need to find test points in each one of those intervals. So the test points are -2, and you don't have to pick -2. I just pick something in that interval. Something in between -1 and 1/2, I'll choose 0. And something greater than 1/2, I'll choose 1. And we want to substitute these test points into the second derivative. Let's see. So we have our critical numbers, or sorry, not our critical numbers, our test points being our x's, and we want to substitute into the second derivative. We've got -2, 0, and 1. So we'll plug that into our second derivative. I'm going to plug it into the factored form of the second derivative. It's usually easier to tell the sign if it's in factored form. Okay, so if I do 6 times 2 times -2 minus 1 times -2 plus 1, I've got a positive times a negative times a negative, and this comes out to be positive. So in this first interval, my second derivative came out to be positive. And I have 6 times 2 times 0 minus 1 times 0 plus 1. And this is a positive times a negative times a positive. So that interval is negative. And the last one, 6 times 2 times 1 minus 1. 1 times 1 plus 1. That's a positive times a positive times a positive. So this last interval is positive. Now, when the second derivative is positive, that tells us that our function is concave up. And when the second derivative is negative, that tells us our function is concave down. So I now know the intervals of concavity. So the function is concave up from negative infinity to negative 1, union with 1/2 to infinity. And it's concave down from negative 1 to 1/2. Finally, we're looking for points of inflection. And finding points of inflection are analyzing this chart that we've already made. And points of inflection are going to occur anytime we have a change in concavity. So right here over the critical number of -1, if we look to the left, we have concave up. We look to the right, we have concave down. So that means that we have a point of inflection at x equals -1. Same thing at the other critical number. To the left, we have concave down. To the right, we have concave up. That creates a point of inflection at x equals 1/2. But we want to write these points of inflection as ordered pairs. So we're going to substitute these values into the original function. So let's substitute -1 into our f of x, and also 1/2 into our f of x. F of -1 being -1 to the 4th plus -1 cubed minus 3 times -1 squared plus 1. That's a +1 minus 1 minus 3 plus 1. So that is -3 plus 1 is -2. So we have a point of inflection at -1, -2. And the other one's going to be a little bit messier because of the fraction. So we have f of 1/2 being 1/2 to the 4th plus 1/2 cubed minus 3 times 1/2 squared plus 1. So 1/2 to the 4th, that would be 1/16. Let me just double check. 2 times 2 would be 4, times 2 is 8, times 2 is 16. Okay. 1/2 cubed, that's 1/8. Minus 3 over 4. 1/2 squared would be 1/4, and 1/4 times 3 would be 3/4. So I'm going to add these guys together, getting a common denominator. Since I've got 16th being the biggest one, I'm going to multiply by 2 over 2, 4 over 4, 16 over 16. You get 1/16 plus 2/16 minus 12/16 plus 16/16. So we've got 1 plus 2 is 3, minus 12 would be -9, and -9 plus 16 would give me 7/16. So my other point of inflection would be 1/2 and 7/16.
So we've got 2 points of inflection at -1, -2, and also 1/2 and 7/16. We want to solve this problem using calculus techniques. We want to find the product of two positive numbers. The product of two positive numbers is 588. And we want to find the minimum where the sum of the first and 3 times the second. Find those two numbers. So we have two numbers. I'm going to let the numbers be x and y. The first number is x and the second number is y. And we know that the product of these two numbers is equal to 588. And we are looking, we'll call it the sum of the first and 3 times the second. And our goal is to find the two numbers that are going to produce the minimum for this sum. So this is our function, this sum, that we want to perform the calculus on because we want to find the minimum value of this. But the problem is that this sum has too many variables in it. So we want to use this other equation to reduce the number of variables. So we have x times y equals 588. I can divide both sides by x. That gives me y equals 588 over x. And I can substitute this into the equation. And now my equation only has one variable. So let's work out what 3 times 588 is. That is 1,764. So now we have a function with only one variable in it, and we can do that calculus on it. I'm going to do one more thing algebra-wise to this. I'm going to write this as x to the -1, so it's a little easier to calculate the derivative. So I'll calculate the derivative. That's 1 plus 1764 times -1 x to the -2. So the 1,764 is a constant multiple. I carried that down. And then I did the power rule on x to the -1. Now I'll write this as 1 plus 1764, that should be a minus, over x squared. So there's my derivative. And I'm going to use the second derivative test to minimize this. I'm looking for relative minimum. I'll use that second derivative test. So I need to find the critical numbers. Critical numbers are where the derivative is equal to 0 or where the derivative is undefined. So I'll set that derivative equal to 0. I'm going to add the 1764 over x squared to both sides. I'll multiply both sides by x squared. That'll give 1764 equals x squared. And then I'll square root both sides. So let's see if that's a nice square root.
Okay, the square root of 1764 is 42. We've got plus or minus. X equals plus or minus 42. Now the derivative is undefined at 0. But 0 was also undefined in the original function. So x equals 0, even though it does make our derivative undefined, it is not a critical number. So we just have one critical number to consider. I'm ignoring the negative 42 because in the directions, if I go back up here, it says that the two numbers are positive, so I can ignore that negative 42. And now I want to find out if this positive 42 is a min or a max, because if it's a min, I've found the numbers to minimize my function. So I'm going to test that into my second derivative. So here's my first derivative. That's 1 minus 1764 x to the negative 2. I'll calculate the second derivative. And that would be negative 1764 times negative 2x to the negative 3. That's going to be a positive, let's see, 1764 times 2. That's 3,528 x to the negative 3, or 3,528 over x cubed. And I'm going to test that 42 into the second derivative. And I know that this is a positive value. When the second derivative is positive, that tells me concave up. Concave up combined with it being a critical number means that I have a minimum. So I just found the minimum value of x to be 42. And I can find the y part, 588 divided by 42, is 14. So the first number is 42, and the second number is 14. These are the two numbers whose product is 588, and the two numbers that create the minimum value for this expression, x plus 3y, the first number plus 3 times the second number.
Thank you for checking out my videos. Have a great day.